In this presentation, I'm going to explain about one cycle control, OCC of buck converter, and here the basic working of control technique of one cycle control, and comparing the performance of one cycle control with the conventional PI controller. Therefore, we are considering a buck converter, and the control technique what we are doing is here is one cycle control, OCC. Now I'm just reviewing what is the buck converter. It is a step-down converter, and the circuit topology or circuit diagram is shown here. At the input side, there is a switch, and there is LC filter is there, and there's a freewheeling diode is there, and the load is considered as R is the load. For the input voltage equal to VD, and average output voltage equal to V0. Therefore, here, when switch is on, the corresponding equivalent circuit is shown here. When switch is on here, since it is plus, diode is reverse bias, and the corresponding equivalent circuit is shown here. And the input voltage equal to VD, the voltage across the inductor equal to plus here minus here VL, and the average voltage across the load is equal to plus here minus here V0. Now we are applying the Kirchhoff's voltage law KVL, and you'll be getting it is equal to the voltage across the inductor is equal to the input voltage VD minus V0. Therefore, that voltage VD minus V0 is the voltage that is across the inductor when switch is on. Now, when switch is off here, the corresponding when switch is off here, the energy stored the inductor will be driving the current the same direction, so that the voltage polarity here will become plus here and minus here, or that will be forward biasing the freewheeling diode, so that there will be a current through the freewheeling diode, and the corresponding equivalent circuit is shown here. Now, if you calculate the voltage across the inductor, again applying the Kirchhoff's voltage law here, the voltage across the inductor plus the voltage across output voltage, average output voltage V0 is equal to 0, or VL equal to minus V0. Therefore, when switch is off here, the voltage across the inductor is given by minus V0. Therefore, this is the voltage across the inductor when switch is on as well as when switch is off. And as per the volt-second balance concept, the average voltage across the inductor over one switching period should be equal to 0. Otherwise, the net there will be a change in flux, or delta phi will comes there, and the core will be finally get saturated. Therefore, in order to avoid that one, because the product of voltage and time is nothing but flux, the unit of flux linkage as such. Therefore, this represents this area represents that is the product voltage and time, and that corresponds to the positive flux, and this is called a negative flux. So the net flux change after one switching period should be equal to 0. So for obeying that, we get VD minus V0 into T on, or this area, plus minus V0 into this TS minus T on equal to 0, or we'll be getting VD into T on equal to V0 into V0 into TS, or the output voltage, average output voltage V0 equal to V0 by VD equal to T on divided by Ts equal to D, or V0 equal to D times VD, where D is called the duty cycle. Therefore, this is the basic equation of average output voltage of a buck converter. Now, in the closed loop control of buck converter, of course, in this case, what we are considering is a PI controller. First, we'll be considering a PI controller. This is the buck converter, that is a simulating model access. And this is the buck switch. This is feedback diodes. This is L and C. This is the low pass filter, and this the load as a resistor. Therefore, this is the input voltage shown as this one. And here, what we are sensing the output voltage, and that is compared with the reference voltage, and that is given to a PI controller. But we are taking Kp and Ke as 0.1 and K as 1. That is by trial and error it is fixed, and it is tuned as such, and that output of that PI controller is compared with a sawtooth waveform, and that output of that comparator is given to as input switching signal to the switching device or MOSFET. Therefore, here the output voltage will be getting the same as the reference voltage, independent of the input voltage perturbation. Here, input voltage is changing from 15 volt to 20 volt, and the reference voltage have been kept as 6 volt. We can see that one, even though the input voltage is changing, perturbation is there from 15 to 20, we'll be getting the output voltage as 6. And we'll be seeing that output voltage in response in the next slide. This is the simulating model of a closed loop control of buck converter using a PI controller. For the closed loop control of buck converter with input voltage perturbation or line regulation, the input voltage is changing from 15 volt to 20 volt. That input voltage is 15 and then suddenly changing to 20 volt. And the reference voltage what we kept is equal to 6 volt. For the output voltage here it equal to 6 volt. Then suddenly when the input voltage is changing to 20 volt, there is a sudden rise is there. That is after that settling time, it is settling to the reference voltage 6 volt. Therefore, this is the output voltage of course response corresponding to an input voltage perturbation from 15 volt to 20 volt. This is the output voltage, and since the reference voltage is kept as the 6 volt, and the Kp and Ka selected as tuned as is by trial and error. The Kp, that is proportional constant 0.1, and the integral constant is taken as 1. Now already we have seen the PI controller, and what the inference is that PWM control using PI controller. In PWM control using the PI controller, the duty ratio is modulated in a direction that reduces the error. Therefore, that is modulated. The PWM is modulated in such a way that reduces the error, means that whatever the output voltage is coming into the reference voltage, so that the error is being minimized. When the input voltage is perturbed, that for example, if suddenly the input voltage is changing, say for example 15 to 20 like this one perturbed, that must be sensed as an output voltage change, and the error produced in the output voltage is used to change the duty ratio to keep the output voltage to the reference value. For whenever there's a perturbation is there, that will be causing a change in output voltage, that is sensed and that is compared with the reference, and based on that one, that is the output of this in the here output of PI controller changes, and that is compared with that one, then that is controlling that will be changing the duty cycle. But that will take, this means that it has a slow, the output voltage to reference value. This means that it has a slow dynamic response in regulating the output in response to the change in input volt. It takes few cycles to get stabilized in a PI controller. Therefore, now we'll be explaining the another type of control that will be concentrating, that is one cycle control technique, in which the response is faster than the PI controller. Now let us see what is meant by one cycle control or OCC. It is basically a non-linear control technique is used here, and uses the concept of control of average value of the switching variable. Now we'll be seeing in that one. Here the average value means that when, for example here, when the switch is on, the input voltage is VD will be available at this point, and when switch is off, the output voltage equal to 0. That is in a buck converter, already we have explained that one. Therefore, then we are taking that is passing through a low pass filter. The purpose is that we have to extract the average voltage, or the DC component is to be extracted. That is extracted, that will be available at the output. Therefore, LC filter is a low pass filter that will be extracting the average voltage that is coming across that one. Therefore, the concept of control of average value of switching variable, in that case here, the OCC can be used here. One cycle control technique can be used. Basically, one cycle control one, that is within one cycle that gets controlled as such, because that it reaches the reference voltage. Output voltage reaches to reference voltage. For example, the different parts of the OCC components are, this is the OCC, that is one cycle control block as such. The different parts are, there are 4 parts. One is called the resettable integrator. This basically is an integrator. It's shown as an op-amp based integrator, and this can be reset also. There's a switch across the capacitor so that when it is on, that can be reset. Therefore, it is a resettable integrator. That's the first part. Second one is a comparator. There's another output of the integrator is given to the comparator. Another input is the reference voltage. Therefore, the second one is the comparator, and the third one is the SR flip-flop. Set reset flip-flop is that is the third component, and the fourth component is the clock. The clock is given to the set pin of the SR flip-flop. Therefore, these are the 4 components of one cycle control, which is equal to resettable integrator, a comparator, an SR flip-flop, and clock signal. And we'll be seeing the working in the coming slides. Therefore, this is the power circuit, buck converter power circuit. And this voltage is sensed, and that is given as an input, that is integrated, that is compared, and that is compared with the reference, and that is given to the reset pin. We'll be working in the coming slides, the working of this OCC in the coming slides. Now let us see the working of one cycle control for a buck converter. Now let us see this is the power circuit as already explained. The input voltage equal to VD, average output voltage equal to V0, and this is the feedback diodes. The L and C forms the low pass filter, and this is the switch. Therefore, this represents the power circuit, and the bottom one we call it as control circuit. That is the one cycle control. Components are resettable integrator, comparator, SR flip flop, and the clock. Therefore, this is the, I shall explain the working as such. Now, when the clock signal is coming rise, that is when the clock signal is coming to the set pin, a rise pin at this point, then this Q will become high and the switch gets turned on. Once the switch gets turned on, this point voltage will become same as the input voltage. For that is here the voltage at this point, that is the V in, it is marked as V in will be same as the VD, and that VD is given as an input to the integrator. It's a resettable integrator. It is, of course, that is given to the inverting terminal of that one. When a constant is given to an integrator, is, you know that output is a straight line. Therefore, but since it is given the negative input, because V integrator equal to minus 1 by RCF integral V in dt, or it is equal to minus of V in R1 CF into T. This is a constant, V in divided by R1 CF is a constant. Therefore, the equation is a straight line equation, y equal to mt, like that. Y equal to a constant, V in T equal to a constant slope, that is V in divided by R1 CF into T. It's a straight line equation, of course, with a negative slope. Therefore, the integrator output is shown here. It is having a negative slope here. And that is compared with the reference. Whatever the reference means, so for example, if you want to get, say, 10 volts here, and here 10 volt is given, that's a reference voltage. Therefore, once that voltage reaches to the reference voltage, but the output of the integrator reaches to the reference voltage here, then this reset pin will become high, or reset pin will become high means that is reset, signal will become high, and that will be R will be high. When R is high, Q will become low and Q bar will become high, or Q bar is high. When Q become low means the switch gets turned off. Therefore, at this instant, the switch gets turned off, and this voltage will become zero, because the diode is conducting the voltage across at the input here, V in will become zero. You'll be getting a zero voltage. And here at the same time, the Q bar is high means that is given to reset the integrator. Because this will be high, that will be closing the switch, or the capacitor charge is getting reboot, or that will be resetting the integrator. Both will be done by this Q bar, as well as Q is the switching off the device. Then here, the getting turned on will happen in the next clock signal. The next clock signal, again, that is at this point, next clock signal, here the Q will become high, and the device, that is the power BJT, that gets turned on. Therefore, that gets turned on. Therefore, that here on period is being fixed by the duration for which the integrated value is reaching to the reference. The remaining one is the off period. Then again, it has the switching on, that continues. And the average value of this voltage, whatever the voltage coming this reading, the average voltage will be available as the output voltage, same as the reference voltage. Therefore, this is the way in which this is working. And the duty ratio of the switch is controlled in such a way that the average value of the switch variable means the voltage at the input side, voltage input to the low pass filter or across the freewheeling diode, that variable is equal to or proportional to the control reference voltage, because we want to make a voltage which is equal to same as the average value of this one, which is equal to the we are making that reference voltage, and the average value will be getting at the output same as the reference voltage. And the output voltage of the buck converter is the average value of the switched variable. That is, in this case, it is equal to V in, but the same as if you take this point at this point also. There's no difference, as we'll be while doing the simulation. We can take this point to here also. It will be same in that case. Therefore, the output voltage of the buck converter is the average value of the switched variables V in. Therefore, this is the different switching signal or different signal as such, and this is a clock signal, and this is the output of this SR flip flop. Q signal is this one, and here this is the input voltage at this across the diode V in, and this is the integrator output that is compared with the reference voltage. Once this integrator output is reaching to reference voltage, here the signal gets high, or R will become high, then Q bar will become low. This is getting turned off. The same time, this is getting resetting also. So this is a resettable integrator. Now continuing the buck converter using one cycle control here. This is the same circuit as already I explained that one. This is the power circuit and this is the one cycle control. This one is taken and it is integrated by a resettable integrator that is compared with the reference, and the output is given to the reset pin and the clock is given to the set pin, and working I already explained in the previous slide as such. And the voltage across the diode that is shown here, that is the voltage across the diode. Actually, the output voltage is the average value of the voltage that is coming across the diode. That is why we are connecting a low pass filter that passes, that will be rejecting all the harmonics, and that will be passing only the average value or DC value of this signal. Therefore, this is the average value of the signal that is available across the load. Therefore, average value of this voltage is nothing but integral. If we are integrating this one, this area is distributed over this time period, or integral V in dt divided by Ts, where this integration time constant, that is R1 and Cf, is called the integration time constant. Now if you integrate this one by in this integrator, the equation is that V integrator equal to minus 1 by R1 Cf integral of this voltage V in T dt, or this constant, this I am referring 1 by R1 Cf, I am taking it as a constant K, or minus K integral V in T dt. And here that is the integrated output, and here this is the average value of the voltage equal to this. And to here comparing these two things, here we can see that one, the time constant of the integrator is chosen as, that is the time constant which is equal to R1 into Cf, that is chosen as this product, no, R1 into Cf is chosen as the same as the time period, that is the clock time period Ts. For the clock time period, for the time constant of the integrator is chosen as the time period of the clock signal. That is the condition to be satisfied. The R1 into Cf should be same as the time period of the clock Ts. Now let us see the working of a buck converter with one cycle control, in which the input voltage is perturbing, or that is changing. That is, here the input voltage is, previously this was the input voltage, suddenly it is changing to that one. How the system is behaving, let us see that. What we want to get is that instead of, even though there is a change in input voltage, output voltage you want to same as the reference voltage. Therefore, here this is the input voltage variation, and here you see that a reference voltage is this one. This is the voltage that we want to output is this one, and here you see that one. This is integrator. This in the whatever this voltage, no, that input voltage, that same as the source voltage, that voltage is being integrated by this one. Of course, that when you are integrating a constant voltage, it will be linearly with a because since it is given to a inverting terminal, it will be having a negative slope. And once that reaches to the reference voltage, what we are giving the reference voltage here, then this is switched off. That is switched off, and therefore this period is equal to switch on period, and this period is equal to off period. Therefore, this is the off period, this is the on period for a the voltage of this much. Now, if the input voltage is suddenly increasing to this and a new value here, since as you know that one, again the input voltage is same increasing here, the integrator output voltage, if you see the integrator output voltage equal to minus 1 by R1 Cf integral V into dt, or in V into T divided by R1 Cf minus into T. Or since input voltage was previously it was this much, but now it is increased here, means that the slope is, now we can see that slope is increasing, because V in is increasing here, the slope is increasing. That is why once the voltage is increasing at this point, the slope is increasing, means that is again the compared to this one, the slope is increasing, or that is reaching to the reference value just before that one, meaning that this is reaching to that means on period is, of course, on period is reducing and off period is increasing. Therefore, then again the output voltage is same as the reference voltage. Therefore, as the input voltage perturbation occurs, you can see that from this itself, the slope of this integrator output, that slope is increasing because V in is increasing, and we can see that that is reaching the the reference earlier, so that the on period reduces and off period increases, and thereby duty ratio is reducing, so that again, even though there is an increase in input voltage, duty ratio reduces and the output voltage will be the same as the reference voltage. Therefore, that is the here the input voltage perturbation will immediately causes a change in the slope of the integration, because being increasing, the slope is increasing with one switching period. As a result, the duty ratio changes and the output voltage do not change even if the power source having a voltage disturbance, because if there is a disturbance at the input side, the output voltage does not change, because this the slope of this integration when it is increasing, integration is increasing and the on period reduces, so that the duty ratio reduces. That is if the input, and here we can see that one, if the input suddenly increases, the slope of the integration of the output, and that is this one, that is Vin divided by C1 RF, increases and it reaches the reference voltage, that is it reaches the reference voltage, that is here. Once it reaches to reference voltage, that is getting switched off. It increases and it reaches the reference voltage V reference. Early and on period reduces and off period increases, leading to the reduction of the duty ratio. The duty ratio reduces, and again, even though there is an increase in input voltage, since the duty ratio reduces, the output voltage is same as the reference voltage. That is the voltage perturbation rejection of a one cycle control of a buck converter. Now, when the reference voltage changes, what happens? That is, the change in reference voltage with a fixed input voltage. Input voltage is constant, but the required reference voltage is suddenly changing. Previously, this was the reference voltage. Suddenly changes here means that again here the reference voltage changes. The slope of integration, as already we have seen, it is equal to minus of V in divided by R1 into Cf. Therefore, input voltage is not changing, but the reference voltage is changing. Since the reference voltage is changing means that this slope is not changing, because there is no change in input voltage. But since it's having the same slope, but the reference voltage is increasing means that in this case you can see that one, as the reference voltage increases, the time to reach the reference voltage increases. Previously this was the time, but now it is increased. That is why on period will be increasing and off period will be reducing, or duty ratio will be increases. Therefore, as the reference voltage increases, the duty ratio increases and the output voltage will be reaching to the same as the reference voltage. Therefore, here when the control reference is changed by a step, the time taken to reach the new control reference signal, that is new control, but here that slope of the integration remains the same, but more time takes to reach the reference voltage, meaning that the on period will be increasing and off period will be reducing, or the duty ratio will be increasing. And duty ratio is larger as control reference voltage increases. When the control reference is lower, the duty ratio is lower. And as an example, assume the input voltage equal to 20 volts. Initially reference voltage is equal to 10 volt. Then the duty ratio is given by, because output voltage equal to 10, input voltage equal to 20 means duty ratio equal to 0.5. When the reference voltage changing from say from 10 to 15 here with the same input voltage here, you can see that the duty ratio will be between that. Now the output voltage equal to 20 and input voltage equal to 15 means the duty ratio or duty cycle that will become 0.75. Therefore, output voltage becomes output voltage will become 115. Because input voltage equal to 20, the duty cycle now it is increased from 0.5 to 0.75. Now the output voltage reaches to the reference voltage 15 volts. Therefore, that is the how the one cycle control is working as the reference voltage changes. As the reference voltage increases, the duty ratio increases. As the reference voltage reduces, the duty ratio reduces. Now we'll be seeing the general procedure for implementing on-cycle control. This can be this is a general statement that can be used for buck converter, boost converter, buck boost converter, any type of converter that can be used. So this is a general procedure. First thing, write the voltage gain equation, that is V0 by Vd, that equation in terms of D, duty ratio or duty cycle. For V0 by D equal to D, that for a buck converter, the basic equation is that V0 by Vd equal to D. If it is a boost converter, we have to see V0 by Vd equal to 1 by 1 minus D, whatever that converter. You first write the corresponding voltage gain equation, V0 by Vd equal to D in case of buck converter. Since now we want to get an output voltage same as the reference voltage, we replace the V0 by V reference. Therefore, the next equation will become V reference divided by Vd equal to D. V reference divided by D equal to D. because we are replacing the output voltage same as a because we want the reference voltage V reference, it is replaced by V reference. For V reference divided by Vd is equal to D, or V reference equal to D times Vd. That is the second step. Third step is combine the terms having the D and not having the D. In this case, there's no problem. This is the term which is not having the D, and this is the term which is not having the D, and this is having the D. So that is combining that one. Therefore, the term D is replaced by, now D is replaced by 1 by Ts integral 0 to on period, or whatever that one, that into dt. For in buck converter, it is equal to, since V reference equal to dVd for a buck converter, that is represented as, that is, it is equal to, D is replaced by 1 by Ts integral 0 to on period into whatever this Vd into dt. That is the reference voltage. For V reference is equated to this one. The term D is replaced by this one. Therefore, the buck converter, it is V reference equal to dVd, or 1 by Ts integral 0 to T on Vd dt. Continuing the general procedure, combining the term having D is given to the input to the resettable. That is, whatever the terms inside D, for example, in this case, D means the Vd is the input. Vd can be given, in this case, though it is given from this point, it is equivalent to taking a point at this point. Both are equal. Therefore, the term that is having the D, that is given when I have simulated, I have taken from this only. Both this will also will work. Therefore, here the term having D, that is given to the resettable integrator. And in buck converter, Vd is given as the input to the resettable integrator. Instead of Vin, Vd can also be given as the input to the, you can give the Vin or Vd, both will work together. In that case, that is given to the input to the integrator. And this integrator output is given to the positive terminal of the comparator. This integrator output is given as the positive input to the comparator. Then the term having no D, that is the combined term that does not have D, that is given the negative terminal of the comparator. In this case, this is the having not term, the reference. Therefore, that reference is given as the negative terminal of the comparator. And in this, in buck converter, the reference is given to the negative terminal of the comparator. And the output of the comparator is given to the reset terminal of the SR flip-flop. The output of the comparator is given to the reset terminal of the SR flip-flop. And the clock signal is given to the set terminal of the SR flip-flop. This is given to the set terminal of the SR flip-flop. And we are taking the clock's time period, that is this Ts, same as the time constant R1 into Cf. The clock time period of is same as the integrator time constant. And Q terminal of the SR flip-flop, this Q is connected to the, it is given to the switch. It is given to the switch, and Q bar is given to the reset pin, reset switch of the integrator. That's Q bar is given to the reset, that is this switch is given to the this pin or resetting of this integrator. That is, by closing this one, the capacitor is discharging, and that is called, that is given to the resetting of the resettable integrator. Therefore, that is the general procedure to implement the one cycle control. And this is as far as the in the buck converter is considered, this is the way in which we can connect. Now let us see the implementation of it. This is a simulating model of this implementation of buck converter with a one cycle control. And here, input voltage is changing from 15 volt to 20 volt, and we are keeping the reference voltage to 10 volt. We are keeping the reference voltage to 10 volts, and the input voltage perturbation is done from 15 volt to 20 volts. And this is the power circuit. The switch is there, of course, feedback diode is there, inductor is there, LC filter is there, low pass filter, and the load is there. Therefore, this is the power circuit. And here, as already explained the general procedure, what we have to do that, V reference equal to dVd. For whatever component along with the D, that is to be given as an input to the resettable integrator. Therefore, here means Vd is to be given as the resettable integrator. Therefore, here this is the resettable integrator, and to that one we are taking from the input voltage, that is taken as the from the input voltage, that is K, and that is integrator. And of course, here a multiplication is to be done, because this is a purely the time constant is to be taken care, and for that one we have to multiply here, because V integrator equal to minus 1 by R1 Cf into V in T dt, or that is equal to K, constant K into V integrator T, or we can see that the time constant R1 Cf equal to, this time constant is same as the time period of the clock. Therefore, we are selecting a clock period, clock frequency as 10 kilohertz, or the clock period as 1 by 10 into 10 raised to 3 or 0.1 milliseconds. Therefore, we are selecting this R1CF same as TS, which is equal to 0.1 milliseconds, or therefore the constant K is nothing but it is equal to 1 by R1CF. Therefore, 1 by K equal to 1 by R1CF means 1 by, here R1CF is taken as, which is equal to clock time period 0.1 or 1 by 0.1, or that is 0.1 millisecond, which is equal to 10,000. Therefore, we are selecting that constant. This constant is as the 10,000, since we are selecting the clock frequency as 10 kilohertz. Therefore, that is given as an input to the comparator, positive input of the comparator. To the negative, we are giving the reference signal, because the reference signal we are selecting as the 10 volt is the reference signal, and this is the comparator, and the comparator output is given as an input to the reset pin of the reset flip-flop, SR flip-flop, that is reset pin of the SR flip-flop, that is given. And to this one, to the clock is given, the clock signal is given, and that is given as to the set pin of the SR flip-flop, and the output Q is given as the input to the switch, and here Q bar is used to reset this one. Q bar is used to reset the resetable integrator. Of course, a delay is to be given. Therefore, this is the one cycle control block as such, and this is the power circuit, and here the constant K is selected as 10,000 because the clock period is taken as 10 kilohertz. Therefore, this is the Simulink model of a one cycle control of buck converter. Now let us see the response of that buck converter with a one cycle control here, input voltage and output voltage. And this is the input voltage variation. It is changing from 14 volt to 20 volts at this instant. For input voltage perturbation is done, but the reference voltage we are kept as 10 volts. What we want the output is always 10 volts. Therefore, the reference voltage is 10 volts. We can see that one. This is the output voltage. Even though there's a perturbation at this instant, slight increase is there, but finally that reaches to again 10 volts. Therefore, that is rejecting the input voltage perturbation. As I already explained, the input voltage perturbation is being rejected by the one cycle control, even though the input voltage is changing from 14 volt to 20 volts. Since the reference voltage is kept as 10 volts, we'll be getting the output as 10 volts. Now let us see compare the performance of this comparison of OCC and PI controller when input voltage perturbation is there. Already we have seen the input voltage perturbation is there. This is the output voltage with OCC. But with the PI controller, we can see that one, the overshoot is more also, as well as settling time is also more here. It is, the overshoot is less here in one cycle control, but that is more in the PI controller, and the settling time also increases when the input voltage perturbation is there. Because the reference voltage we are kept as this one is a 10 volt, and the input voltage perturbation is changing from here 15 to 20 here. And this is the output voltage with one cycle control, and this is the output voltage with the PI controller. And if you compare the performance, like the settling time, it is 3 milliseconds, and here PI controller it is far more, 35 milliseconds. Therefore, this is the input voltage perturbation is done here, and this is the output voltage with one cycle control, and this is the output voltage with PI controller. Therefore, the settling time is quite more in the case of PI controller compared to OCC. Now, buck converter using the one cycle control with a reference voltage change. For the reference voltage we are changing, we are keeping the here, we are not disturbing the input voltage, but reference voltage, the required voltage we are suddenly changing from 10 volt to 14 volts. Now, same circuit, this is a power circuit of a buck converter, same as I already explained here. The input voltage is sensed as that is given as to the resetable integrator, and this is a gain which is already 10,000, as we already seen that, because the time period equal to of course frequency equal to 10 kilohertz and time period equal to 1 by 1 by 10 or 0.1 millisecond. Based on that one, K equal to 10,000, and this is the reference change. For this is what we want. We want to change the reference output voltage from suddenly in this fashion. So for that is given as the reference voltage, that is given to the negative, and this is given to the positive terminal of the comparator, and the output of the comparator is given to the reset pin of SR flip-flop, and clock is given to the set pin, and again the Q is given to the switching of the switching input to this MOSFET, and the Q bar is given to the reset pin of the resetable integrator after providing a delay here. Therefore, this is the power circuit, and this is the one cycle control technique or method, or this is the reference change happens from 10 volts to 14 volts. Now let us the performance comparison of OCC and PI used in the reference voltage change. See, for example, here the reference voltage is changing like this one. It is changing, the required voltage is changing from, say, here changing at this fashion. And here we can see that one, the output voltage of OCC is changing like this one. But with PI controller, it takes more time to reach the reference voltage. For the settling time, again, that is much higher in the case of PI controller compared to the one cycle controller. As the reference changes here, of course, the output should track the reference voltage, but it takes more time to reach that reference voltage in the case of PI controller compared to the one cycle control. Therefore, this is the reference voltage first, and this is the output voltage with using the one cycle control, and this is the output voltage with using the PI controller as the reference voltage changes. Thus we can see that the one cycle control method is having better performance compared to the PI control that we are seeing for a buck converter. And even this one cycle control method can be used to any type of controllers. We'll be seeing in the next presentation for a boost converter, buck boost converter, etc. The basic concept of implementing that one is already I explained that method of getting the signal to the resetable integrator and the signal to the reference signal. Once given, the same circuit can, that control circuit or one cycle control technique is same.